The central challenge of software engineering is translation. It takes the abstract, chaotic needs of a business, converting them into a precise technical architecture. To bridge this gap, the discipline is divided into two distinct halves. Systems analysis. This phase strictly investigates the problem to answer one question: what must the system do? This diagram shows the required pivot to systems design. Once the what is established, design dictates exactly how the system operates. Older predictive models finished analysis before design began. Modern Agile development abandons this approach for a continuous, iterative loop between the two. A monolithic predictive approach forces engineers to spend months making assumptions. Without iterating, they cannot test if their theoretical how actually solves the business's what until the end of the project, when it is too late to change course. Consider the case of Ridgeline Mountain Outfitters, or RMO. Their field purchasing agents need a custom application, a trade show system, to log inventory on the showroom floor. Every system originates from an artifact like this, the system vision document. Examining the problem description reveals the core business driver. Agents currently lack a way to communicate rapidly with the home office about the products they are evaluating. From this, we can extract a specific, verifiable system capability requested by the stakeholders. The application must capture and store information about manufacturers and suppliers in real time. But a programmer cannot write code from a paragraph. This vision document must be systematically dismantled and translated into explicit technical constraints before development begins. This chart maps out an SDLC iteration. It defines a bounded time box where all 6 core system development processes are executed to build a small, functional piece of the target system. This flowchart tracks the engineering team through a single 6-day Agile iteration. Day 1 focuses on planning. The team defines functional requirements, actions the system must perform, and non-functional requirements, dictating qualities like security and response times. To scope the iteration, the team isolates one component of the wider application. For these 6 days, they will build only the supplier information subsystem. This document is the work breakdown structure. It assigns strict hourly estimates to the remaining SDLC phases to ensure the sprint is achievable. By locking the schedule and the scope on day 1, project planning isolates variables. It prevents scope creep and ensures the team builds only what is strictly necessary for this specific iteration. Moving to day 2, the team enters the systems analysis phase. Their sole objective is determining exactly what the supplier information subsystem must do. Systems analysts do not write code. They conduct preliminary fact-finding, interviewing the purchasing agents to discover the real-world business details. They model these interactions using an activity diagram, mapping the precise sequence of decisions and actions a user takes when evaluating a supplier. Workflows are codified into a formal use case. The broad capture supplier info becomes a specific action, look up supplier, initiated by an actor. Concurrently, analysts identify object classes, establishing dedicated database entities to hold data for both the supplier and the product. Day 2's analysis phase strips away human assumptions and ambiguous language. It leaves the team with a verified, logical model of the required system behaviors. Days 3 and 4 represent the critical pivot. We leave analysis and enter design. The team must now decide how the system will technically achieve those mapped use cases. For enterprise applications, engineers rely on the 3-layer architecture. The top plane is the presentation layer, the user interface dictating screen layouts. Below it sits the business logic layer, which processes rules, calculations, and validations for submitted data. At the foundation is the data layer. This requires rigorous database design, structuring tables and primary keys to normalize the supplier records so they can be stored efficiently. By isolating these layers, engineers can redesign the top user interface without accidentally breaking the database mechanics at the bottom. On day 5, the architecture is approved, and the programmers begin coding the actual layers. The code is structured using object-oriented design, or OOD. This bridges the gap by turning the logical analysis models directly into programmed classes. High cohesion ensures a block of code focuses entirely on a single specific task, rather than entangling multiple functions together. Low coupling minimizes dependencies between modules, ensuring that a failure in one area doesn't trigger a cascading collapse across the system. Writing code with high cohesion and low coupling guarantees that the RMO trade show subsystem is robust enough to survive the addition of future iterations. On day 6, the code is written, but it must be rigorously verified before deployment. The developers first run system testing to prove the code technically works end-to-end. This is followed by user acceptance testing, where the client verifies that the working code solves their original business problem. The final output of this 6-day sprint is known as a walking skeleton. It's a basic working version demonstrating end-to-end functionality, successfully moving data from the user interface down to the database and back. The goal of the first iteration is never a final product. It is the establishment of a proven technical foundation. Zooming out, we see the broader lifecycle. With iteration 1 complete, the team immediately loops back to core process 1, beginning iteration 2 to target the next subsystem, like product information. This cycle mitigates risk. By working in rapid bursts, the team confronts analysis, design, and deployment realities repeatedly, catching errors early. Modern enterprise systems are not engineered in a single monolithic effort. They are grown, piece by piece, through the rigorous execution of the SDLC loop. On day 6, the code is written, but it must be rigorously verified before deployment. The developers first run system testing to prove the code technically works end-to-end. This is followed by user acceptance testing, where the client verifies that the working code actually solves their original business problem. The final output of this 6-day sprint is known as a walking skeleton. The walking skeleton is not a polished, finished app. It is a basic, working version, demonstrating end-to-end functionality, successfully moving data from the user interface down to the database and back. The goal of the first iteration is never a final product. It is the establishment of a proven technical foundation. Zooming out from the 6-day sprint, we see the broader life cycle of the RMO system development. With iteration 1 complete, the team immediately loops back to core process 1. They begin iteration 2, targeting the next subsystem, like product information. This iterative cycle mitigates risk. By working in rapid bursts, the engineering team is forced to confront analysis, design, and deployment realities repeatedly, catching errors early. Modern enterprise systems are not engineered in a single monolithic effort. They are grown, piece by piece, through the rigorous execution of the SDLC iteration loop.